20 minutes. So, so I will talk about proposed upgrade of our facility, but I also mention state of the art and current state of the art of our lead plating technology and some resonators update on multi-stop cavities. And then I will just discuss our choice of niobium coated quarter wave resonators for proposed upgrade of our facility. And discuss briefly some other possible thin films SRF applications which can be used in our facility and in other facilities. All right, so we are a little small players in accelerator world. So at Australian National University we have electrostatic peritron tandem accelerator, 14 UD, with one of the first machine built by NEC, and actually it operates up to 15.6 megavolt. So the beam accelerated in the tandem is injected to the different locations. We have total 7 beam lines, and one possible application is the beam can be injected through the superconducting linear accelerator. This accelerator actually was transferred from Desbury about 20 years ago. And actually Desbury electrostatic is still there. Okay, so so we can proudly announce that our LINAC, which comprises only 12 split ring resonators, is a larger scale application of superconductivity in Australia. And so far, probably we are only remaining players in lead plating of the superconducting technology. But actually in our application it works very, very well. So LINAC, once again, is comprising of 4 cryostats with 12 split ring resonators. There is also room, another leg of LINAC. Actually, initially, the room was almost double in length. It was cut by Director 20 years ago and sort of allocated for some other applications. So it's just, but we still have room to install additional 4 cryostats. So we have room for expansion. Okay, so when I heard presentation about Charles, if you start dreaming, so actually these numbers you presented in your talk would be really excellent to achieve, like 5 million per 100 megavolt acceleration gain. Let's say if I will get 20 megavolt, it's 1 million paid for 20 megavolt of acceleration gain, I would put this money on table and go ahead. And actually replaced all this resonator, all half of LINAC and populated another half of this LINAC. So this sounds good. But if we look at Enzo comment that we should look at big players and achievers in this area, so we're also doing very well in this area because the LINAC was upgraded and replated based on John Noy lead plating technology using methanosulfonic acid. So it was really, really successful project undertaken 5 years ago. So right now, when we are talking about the upgrade of this LINAC, so with the small lab, small players, and it's another comment why we don't actually introduce thin film technology in industrial commercialization. So probably it's just all about market and how many people actually can utilize this technology. So in our case, it's obviously when we're talking about upgrade of the LINAC, so we have room for 4 cryostats. So initially, first stage will be to install another 1 or 2 cryostats with 8 resonators. We are talking about this sort of money which we have from fundings recently. So certainly first choice would be in our case, and correct me if I'm wrong, I want to discuss all these options, that I would prefer actually copper, niobium sputtered quarter, copper, something like quarter wave resonators, because in our application is first of all, as we mentioned, not sensitive to the Earth's magnetic field, for instance, with this technology. niobium on copper is also less sensitive to helium pressure variation. Actually, in previous talk, I was surprised quite high pressure sensitivity. So quarter waves probably can be made really non-sensitive to pressure variations. So in spite of the high energy content in such resonators, probably you don't need a very complicated RF system. Like in Triumph ISAC facility with bulk niobium cavities, you still need about, we are talking about kilowatts range amplifiers, RF amplifiers. So in this technology, niobium on copper, probably you could just use a couple hundred watts amplifier, you're still in business. And this also reduce overall cost. So for such lab as our lab, this is really a relatively straightforward choice. Okay, but let's just get through our state of the art of. So as I mentioned, this model cryostat with 3 split ring resonators electroplated with lead. So currently, our LINAC can deliver about 7 megawatt of total energy gain to the 14 UD beam. So thanks to Enzo, we already have this very nice, really nice diagram from thesis, Yogi thesis in 77, and it just point to the fact that with lead we can expect a superheated field which is about 1.2 of critical field for this material. So this just table outlining major properties of lead and niobium. With lead, actually, I also trying to find properties of, because we are plating lead tin in our case, so I'm just trying to find this property of these materials without great success. So if you can find or navigate me, so I would be really grateful for this. So let me just skip all the slides because we already had excellent theoretical confirmation. But here we had just point out that actually lead, it can have quite similar surface resistance as niobium. As we know, for low frequency applications, this low frequency range surface resistance is dominated by residual resistance in this material, so we don't have to go to low frequencies. We'll just mention that we have this range of resistance in nano-ohm based on experience from ALPI and Ergon National Lab results for low frequency cavities. So once again in lead, so from Yogi thesis, we still have interesting transition. So there is some transitional field which was contributed by weak links and grain boundaries, and above it was contributed by enhancement by sharp edges. And here I just show you nice steam train which sort of representing lead technology. Okay, so what we've got count which problems at ANU. So very similar structure. It's not much control, electroplating of layers, superconducting layers, so it results in the formation of relatively large grains. So when I try to plate a few micron, 10 micron, usually grains of proportional to the thickness of the layer, and you don't have really much control. And quite often you can also end up with this growing these beautiful structures, dendrites, and so on. So anyway, by walking around all these problems, so we achieved quite nice performance on average of these cavities. Low Q and high Q is still relatively high, and mainly we are limited by field emission. So all our 12 cavities emit a lot of X-ray at few watts RF power. So we are limited by field emission. And probably it's not. It's quite obvious because, as you can see, we have quite sharp film structure. Plus, lead is intrinsically material which is good to emit electrons. As a result of quite innovative approach, so we're still able to coat quite large surface areas of the superconductor and produce a relatively smooth film, but still limited by field emission. Okay, so this is just a few examples of our capabilities of what we are doing. So it's a tumbling process. This is quite interesting shape or color after tumbling of the copper substrate. So all different structures can be treated in our lab. Surface preparation. This is typical plating, high pressure rinsing, nitrogen drying for different structures, quarter wave, like, and split